Hi there, everyone. Today we're going to talk about the plain Jane of probability distributions, and that is the uniform probability distribution. And the uniform probability distribution is very simple. It just says that every possible value of a random variable is equally likely. And in the case of continuous random variables, right, we don't have single outcomes that we can write down, right? We're doing things like measuring temperature or some other quantity that can be, any value in some interval, right? Because it can be like 88.3 degrees. It doesn't have to be 83 or 84 degrees, right? So there's all kinds of values that temperature can take on, and that's the kind of variable we're talking about, right? A continuous random variable. And these distributions look like rectangles. And the idea is that this is describing to us the probability of certain outcomes of a random variable. So we'll call this random variable x. And on this vertical axis, we'll put a little p for probability. So here's an example. We'll take this random variable x to be uniformly distributed on the interval from 3 to 10. So that basically means we're going to have a rectangle. The low end of it is going to be at 3. The high end of it is going to be at 10. And we're going to interpret area as probability, right? Because this is a continuous random variable distribution. And we know that in the case of a continuous random variable, the area that's described by our visualization of this is got to be a total of 1. So that means that this area that's underneath this curve, right? This area of this rectangle is 1. Now the fact that the area is 1, and we know how long the base of this rectangle is, right? It is a distance of 7 from 3 to 10, means that we can figure out the height of this rectangle, right? So 7 times what is equal to 1? Well, 1/7, right? So that means that the height of this rectangle is 1/7. And once we know that, then we can figure out all kinds of stuff about this random variable x. So let's look at a couple of examples. Let's see if we can find the probability that x is between, let's say 5 and 6. Let's say 5 and 7. Well, to do that, we're going to locate 5 and 7 on this graph. So let's see, 3, 4, 5, 6. That doesn't look good. So maybe 7's here and 5's here. And then area is probability in the case of continuous random variables. So what we're going to do is just chop this piece of this rectangle that corresponds to this interval between 5 and 7 and ask, what is the area of this? So the probability that x lands between 5 and 7 is the area of that rectangle. So its length of that rectangle is 2, right? Because this distance from 5 to 7 is 2. And the height of this rectangle is 1/7. So the probability that random variable x turns out to be between 5 and 7 is 2/7. And we can answer all kinds of questions this way. So here's another example. Let's say we want to look at the probability that x is less than or equal to 5. Yeah, less than or equal to 8. So to get that, right, what we're going to do is, again, mark off the region that corresponds to that interval, right? The probability that x is less than or equal to 8, well, the smallest it can be is 3. So that means that it's this whole area, right? And we need to find the area of that rectangle. And the base of that rectangle has length, let's see, 3 up to 8, that's 5. So this probability is 5 times the height of the rectangle, which is 1/7. So we get 5/7. So this is a piece of cake to work with, right? All we have to remember is that area is probability, and that the whole area, if we're talking about a probability distribution, has to be 1. Right? And that's true for all continuous random variables and their probability distributions. One peculiarity of probability distributions for continuous random variables is, well, let me just show you. Imagine we want to know the probability that x actually turns out to be equal to, I don't know, 6. Well, if we're going to follow the kind of examples that we just did, what we're going to do is find the rectangle in that probability distribution that corresponds to x equals 6. Well, here it is, right? It's just that one line. And the width of that line is 0 times 1/7 as the height. And that, of course, gives us 0. So the probability of x equaling 6 is 0. And that's true of any single number. So the probability that x equals, the probability that the value of this random variable after this experiment or whatever kind of thing we're doing is turning out to be any particular value is always 0. Which is weird, because then that kind of tells you, all right, well, if the probability of x equaling any given value is equal to 0, how can the probability of x equaling something be not 0? Well, it has to do with a whole bunch of facts about real numbers and something called measure theory, but it doesn't really matter. The thing that matters for us is that when we work with continuous random variables, we are always looking at probabilities that the value of the random variable turns out to be in some interval. Since I wrote these things down now, let me just write down the notation that goes with them. This probability that x is between 5 and 7 will often be written like this. Right, so that's the probability that x is between those two values. So we're just writing that x is between those two values in our more compact mathematical notation. The probability that x, here we go, probability that x is equal to, less than or equal to 8, we would write that like this. Right, again, just writing exactly what the criteria is in that more compact mathematical notation. And over here, I have already written what it would look like if we were going to write probability that x is turning out to be exactly 6. Okay, so that is what the uniform distribution looks like. Not too exciting, but very easy to work with, and a good place to start when you're trying to learn about continuous probability distributions. Next up is the normal distribution, which is arguably the most important probability distribution that exists, like in the world.